All right, well, welcome to another fun Friday here in vector calculus. This is a huge Friday, by the way. I don't know if you realize the importance of this day, but this is the dead middle of the quarter. We are at the end of week 6, so from here on out, we're downhill. So, yay, we're almost done. That's my optimism. You know, the glass half empty, half full guy. It doesn't matter how much liquid's in there, it's always full. Because remember, air is also a fluid, it exists. Anyway, all right, so we're at the halfway point. We're on our way. Before we dive into change of variables, is there anything people want to discuss or anything from the homework that we want to look at? Real quick, along those lines, just want to let you know the section that we skipped, 376, whichever one it was, about centers of mass and moments of inertia and all that. I moved that one so that it's due next Monday, not in 3 days, but the following, because we haven't had a chance to talk about it. So just realize that that's not on there anymore. Anyway, so are we good with homework? I think we've actually talked quite a bit about the sections other than the one that we're talking about today. All right, well, then I'm going to jump up to the whiteboard and I will see you in just a second. All right, so today what we're going to talk about is getting to if we do transformations of any kind, if we go from rectangular to something else, how do we figure out what the little multiplier is that's in the integral? Is there a way to do that so we don't have to rely on geometry? Because the geometry is kind of a pain, right? So the question is there a way to find that? And if so, how do we do it? What's the process for doing those kinds of things? So first of all, we're going to be looking at one-to-one transformations. So a transformation is basically just changing how we're viewing the world. For example, when we did polar, instead of thinking of things as x's and y's, we were now thinking of them as r's and thetas. And so we basically took the rectangle. Think of this rectangle from rectangular that had a dx and a dy, and we transformed it into a little chunk of a donut. So this was our dr, and this was our d theta, right? So you can imagine the plane. Think about the xy plane. You can split it into a whole bunch of rectangles. Think graph paper, right? Think about just rectangular graph paper. Well, what the polar transformation does is it takes every one of those rectangles and turns it into one of these little arc sections. But you put enough of those together and you still get the entire plane, right? Think about polar graph paper. So you've seen polar graph paper, I'm sure, and you thought of it as concentric circles that were then divided with like radial lines, right? So you've seen like this is polar graph paper. So you probably saw it as the spider web, the circles with the radial lines. But instead, think of it as we're putting together all kinds of these circular arc chunks, right? So here are just a few examples of them. But you keep stacking those together into rings and extend the rings out. And we basically have now changed our viewpoint of the world. Okay, so what we want to do is generalize this and say, well, what if we're not taking rectangles to maybe we're taking rectangles to pentagon or to parallelograms or to triangles or whatever else, right? That's what we want to do. Now, the one-to-one transformations in general are just doing this, but one-to-one transformations are exactly what you remember, right? What does one-to-one mean to you?
Just converting something directly with no need to like really multiply it.
I don't know. That's not what one-to-one means to me. Like I understand what your thought process there is, that there's not like intermediate step or something. But go back to functions. Like, what's it mean for a function to be one-to-one?
Oh, it means it has one output to one input.
Yeah. So it, like functions just have to take something we plug in and give us a unique thing out, right? That's all we need for a function. But for a one-to-one function, that thing that comes out has to come from only one thing that we're plugging in. Okay, so what that means in terms of transformations is that, think about this one little block right here. That this block is only coming from one of the original rectangles in our rectangular world, not from two different rectangles. So that there's a way to go backwards. That you can go from this new spot back to the original one. There's a way to convert it. Okay, so that's all it means to be one-to-one, is that there's a unique way to go from to any of those regions in our future world. All right, so that's all we're talking about when we've got a transformation. So now the question is, what do we do in general? Like, how do we figure out what the little multiplier is to change our area? So basically, we're going to be looking at, if we start with a dA that's in x and y, so let's just say dx dy, and we convert it to something else. I'm going to call it du dv. So u and v are just some other way. But suppose that we do have some sort of relationship between these. So x is some function of u and v, and y is some other function of u and v. So go back to polar. I'm going to reference polar a lot because it's the one that we're familiar with. But go back to polar. Think about with polar, we had x equals r cosine theta and y equals r sine theta. These are those two functions. This is f of r theta, and this one's g of r theta. So I know I just wrote r and theta instead of u and v, but so what, right? The names of the letters don't really matter. But this is what we're talking about, that there is some function that describes the relationship between x and y and our new variables, our new world view. Okay, so what we're going to need then is that in this transformation, we need to multiply by something in here. So like in polar, that was the r. Same thing in cylindrical. With spherical, it was that rho squared sine phi, right? Well, this thing right here, this multiplier, we call it the Jacobian. Named after this guy by the name of Jacob. Don't get a big head there, Jacob. Different guy who came up with this idea. And so it's called the Jacobian. All right, so the question is, how do we find that Jacobian? Well, it turns out it's actually really easy when you know the relationship between x and y and this new u and v. So let me show you how we get the Jacobian. All right, so I'm going to use the book's notation just so that if you're looking at the book, you'll see it. I don't usually write it this way, but they're going to call it capital J, let me just make sure I got this right. Capital J of u comma v. So it's the Jacobian going to the UV world. And the way that it's found is by finding the determinant of the following matrix. All right, so it's dx du, dy du on top, and then dx dv, dy dv on the bottom.
You say those are V's on the bottom?
Yeah, those are V's. I'll try to make them a little more pointy. You may also notice that whenever I draw U's, I put a little tail on them to help differentiate between U's and V's, because I know how much mine look the same. Okay, so this is how we're going to find it. This is the thing that we have to plug in as a multiplier when we do this conversion. So let me show you how this plays out for polar, and then we'll do it for some other transformations. All right, so we had x equals r cosine theta and y equals r sine theta. So for polar, here's how this is going to go. This is going to be the Jacobian of r comma theta, not u and v, but r and theta. So it's going to be the partial of x with respect to r, the partial of y with respect to r, partial of x with respect to theta, and then y with respect to theta. All right, so let's find those. So if we look at x and we differentiate with respect to r, we get cosine of theta. Then if we take y and we differentiate with respect to r, we get sine of theta. All right, x with respect to theta, we're going to get minus r sine theta. And then y with respect to theta gives us r cosine theta. So let's find that determinant. So hopefully you remember for your 2 by 2 determinants, you just do this little cross multiply and you subtract. So you get r cosine squared minus negative r sine squared, which is r cosine squared plus r sine squared. And by now you've seen the miracle of sine squared and cosine squared enough to see that that does just give us r. Ta-da! Okay, so when we did it, I don't know if you remember, but when we did it back, oh goodness, well, it's probably 2 weeks ago now, but it feels like months. If you go back and you look at that, we used geometry to see that it was equal to r, right? We literally did the geometry on the sectors and all that. Instead, alternatively, we could have done this and gotten there. Okay, but this Jacobian idea is very general, very general. It doesn't matter at all how your transformation is set up, like what x equals or what y equals. As long as you've got that information, you can set up these determinants.
That information between the relationship between our x and y and some other conversion, will that generally be given to us?
Yes and no. Sometimes it's given to you. like I would argue in the case of polar, it was given to us, right, when we constructed it. But even if it's not given to us, we can often do it ourselves. So it will sometimes be given and sometimes not. Obviously, when it's given, it's a lot easier. When we have to figure it out ourselves, it's a little bit more challenging, but it's not terrible. And I'll show you some examples of that. Okay, so you guys good with the process? Ish?
Yeah,
Yeah.
I feel it looks pretty comfortable.
Okay, and that's always dangerous though, right? When you're like, oh yeah, it feels good.
Yeah, and then you see like it in a more complex form, and then you're like, oh no.
Right. And this one feels good for a couple of reasons. Well, first and foremost, I'm doing it, right? When I'm doing it, I always make it look easy. When you have to do it on your own, right? So not only is it that I'm doing it, but it's also an example that you're very familiar with, right? We've been playing with polar or its three-dimensional version, cylindrical, for a couple of weeks just in this class, and you've seen it before and all. So this is one that's pretty familiar, right? But it can get kind of gnarly. And yes, Victor, you're right. At least setting this up is just derivatives, which are way easier, right? Partial derivatives are pretty simple. Before I step off this and show you another example, I just want to point something out. Sometimes when you're building these, you can get kind of confused in terms of, well, is it dx dr dy dr, or is it dx dr dx d theta, right? Like you forget which way you change it. Here's the really good news for you. It doesn't matter as long as you're consistent. If you've got dx dx, dy dy, it's going to work out as long as the r's and thetas are together in columns. It's a little quirk about matrices. You may not know this, but if you were to write it the other way, like if instead I had dx dr dx d theta, dy dr dy d theta, right? Notice again, everything is consistent, right? My x's are together, my r's are together, my thetas are together, my y's are together. This is actually what we call the transpose of that matrix, where you swap rows and columns. And the determinant of a transpose is actually the same as the determinant of the matrix itself. So because of that, you can't really go wrong as long as you get it so that the columns have something in common and the rows have something in common, right? Like in this one, you can see it's the dx's and the dy's are in common in the columns. The drs and the d thetas are what's common in the y's, or in the rows. Same kind of thing with this one. So if that just went, don't worry about it. You're just going to see that it doesn't really matter as long as you're consistent. What I do is I usually just start with x, differentiate with respect to both of them, and I either go down the column or across the row, and then I fill the other column or row with the y's. Okay. Anyway, so here's kind of the idea. Here's how we find it. And now we don't have to worry about trying to do the geometry, which is why this is really nice. All right, so let's look at an example here that is not one that you've done before, right? Because polar you've already done before. So instead, let's try this one. Let's say we want to do this transformation, that we're going to let x equal, let's go u squared plus v squared. And we're going to let y be u squared minus v squared. All right, so let's see if we can figure out what the Jacobian would be for this. So if we were to change our function and do the transformation, what would this new integral look like? What would it need in there, right? So let's even do this. let's say we're integrating over some region, f of xy dA. Okay, so let's see what this is going to turn into. So first of all, it's still going to be integrating over the same region. It'll just be in terms of u and v. Now, this is going to be a function in terms of u and v. And we'll go ahead and put here like a du dv. But the question is, what is the Jacobian? All right, so let's set up our matrix to find said Jacobian. So let's start with x, and let's differentiate with respect to u, and then with respect to v. So with respect to u is 2u. With respect to v is 2v. So this was dx du, dx dv. So this is opposite of how I did it the other time. I just wanted to show you that it doesn't matter whether you go across a row or down a column. So that means that the one we need down here is a dy du. All right, so that's going to be a 2u. And then we need dy dv, which is minus 2v. So that's how I have this one set up. All right, so let's find that determinant. So we're going to get a minus 4 uv, and then minus another 4 uv, which is negative 8 uv. So if we were to use this transformation, we're going to put in a negative 8 uv. All right, now, why would we want to use this transformation? I don't know. I can't answer that. But if this were the transformation we were going to use, here's the process. Okay, so it really is that simple. It doesn't change. It's just a matter of doing it with the proper transformation that you were either given or that you construct yourself. Okay, so again, so far so good. All right, so let's talk before we construct one ourselves. Let's talk about why this works. Why we can actually do this. So I'm not going to go through the entire proof, but I'm going to give you kind of the general idea of how this would play out. Okay, like why it ends up being this matrix determinant gives us that multiplier. So basically, here's the idea. We are taking a rectangular region and we're transforming it to a non-rectangular region. Right, so again, imagine that we've got whatever the image is, the region that we're going to be transforming. We break it up into a bunch of little rectangles. We transform each one of those, and they're going to give us something like this. Okay. All right, now, basically what you need to do is figure out the area of this parallelogram. Well, I don't know if you remember, but you can get the area of a parallelogram by finding the magnitude of the cross product of these two vectors. Now, I'm not going to label them u and v because that will get a little too confusing here. Seeing u and v are our transformation, but those are our two vectors. Okay, now They are two-dimensional vectors. Obviously, to cross them, we need to make them three-dimensional. But so that just means that their third coordinate is going to be 0. In terms of the other two, those other two coordinates, they're going to come from where these, or they're going to come from where these corner points get sent by the transformation, right? Well, if you want to think about how they're going to be formed, let's say that this is from we're going from UV world to say XY world. So if we were going to go from corner to corner here, this is going to be U plus some delta U. And then the Y's are just going to be whatever the V is, right? So hold on. If this is UV, this is U plus delta U, comma V, right? And we're going to make that delta U really, really small so that eventually it becomes a little du. Well, that is saying we're keeping V fixed. So that ends up being a differential in the U direction. So I'm just going to call that a little U plus curvy du. And so that's going to be found by taking that partial and multiplying it by du. All right, and then similarly, the other one's going to be a dv, the partial times dv. So here's how this is going to play out then. If we were to call those guys, let me give them names. We'll call them P and Q. So not U and V, they're completely different. So here's how this is going to look then. P, in terms of its components, it's going to be the, well, I should also give you this. Let's say we've got X equals F of UV and Y equals G of UV. Let's actually give names to the functions like we did before. So the P, we need to do a delta U move, but in the direction only of U. So that's going to be a partial of F with respect to U. So FU times delta U. That's the change in that one. But then we also have to see how Y changes. And so there's going to be the GU times delta U. And then 0. And then Q looks similar, except now we're looking in the V direction. So it'll be FV times dV, comma, GV times dV, comma 0. So if you do the cross product on this, what you end up getting is FUGV minus GU times FV times a delta U delta V. All right, well, think about this thing as that determinant of that matrix. We did dx du, dx dv, dy du, dy dv. When you do that determinant, there's the positive bit and there's the negative bit. So it really just comes from looking at the transformations of those individual lengths in the UV world and how they get bent to new vectors in the XY world. and then finding the area of that parallelogram. So this isn't a rigorous proof, but it's kind of the geometry behind it and why it does what it does. Anyway, just take that for this is why the Jacobian works. All right, so now that we've seen why it works, let's try doing one where we're not given the transformation, but we want to see if maybe we can set one up using a transformation and how you decide what that transformation should be and so on and so forth. So here's what I want to do. Let's give me a really simple example. We are going to integrate over this region right here, where we're going to go from 0, 0 to 1, 1 to 2, 0 to 1, minus 1. Okay, so this is our region R. Again, let me give you those points. And just to have a function, how about we are going to look at the double integral over this region of x minus y dA. All right, so first, let's just talk about, do we need a transformation? So do we need a transformation? Do we need to actually do anything?
Not
Differently.
necessarily. We could just integrate two double integrals.
Yeah, it would end up, we just have to split it into two, regardless of which way we do it, right? Vertical integration man, his head and feet swap once we get to 1. Horizontal, his head and feet are going to swap once we hit 0. So we could do it as 2, no big deal, right? And in fact, finding the equations of those things are going to be pretty easy because they're just lines, no big deal, right? Like, what's this top one? Or this one goes from 0, 0 to 1, 1. What's the equation of that?
X.
Yeah, y equal x. How about the one down here?
Negative y equals negative x.
Y equals negative x. Like, boom, we can just start rattling them off. It's no big deal, right? Okay. However, we could do a transformation to make this a lot nicer. And let me show you what that transformation would be. Again, let's go to those equations. So this one was y equal x. This was y equals negative x. This one is going to be y equals x minus 2. I know it's parallel, so it's got to slip a 1, and then the minus 2 just makes it so it goes through the right place. And then this one's going to be y equals minus x plus 2. So check this out. Look at those 4 sides, but let's move the x's and y's together on one side of the equation. So the y equals x is going to be 0 equals x minus y. The one down here is going to be 2 equals x minus y. The other ones, if I move that minus x over, I get 2 equals x plus 2, or sorry, x plus y. And the other one is 0 equals x plus y. So all 4 of those sides have similar kind of forms. And in fact, this is going to suggest our change in variables. So here's what I'm going to do. I'm going to let u equal x minus y, and I'm going to let v equal x plus y. If I do that, then these 4, the boundaries, they change to being u equals 0, u equals 2, v equals 2, and v equals 0. And so if we now look at this on a UV plane, there's my region. So by this transformation, using this one I just put in green, it turns this region into a square. And talk about easy, the bounds on both of these are going to be 0 to 2. So this is the sort, again, this is probably not one where we would do this because it's fast enough just to do that as two separate integrals. But it's a simple enough shape so you can see how quickly it becomes a nice, easy shape over here. And this is what this integral is going to start looking like now. Let's start converting it. So we need to change this stuff into u's and v's. Well, x minus y, that's equal to u. So we're going to integrate u. We still need to insert a Jacobian. So I'm going to leave a space here for the Jacobian. And then just for the sake of doing something, how about we do du dv, but our bounds are 0 to 2, 0 to 2. So this is shaping up to be pretty nice. It's really a question of what does that Jacobian look like, right? The Jacobian could screw us over, but barring something funky in there, this is going to be a super, super easy integral.
Does that happen? The Jacobian screwing you over?
The Jacobian can be pretty gnarly, for sure, depending upon how you do the transformations. This one, since the boundaries are lines, you're going to see the Jacobian's no big deal whatsoever. But like, think about the one for spherical. We have that rho squared sine of phi. That can really kind of gum up the works a bit, right?
Yeah.
You can imagine if we already have some sort of function with phi, and then now we're going to have to do integration by parts, and Lord knows what it's going to lead to. So can it? Yeah, it can. Usually it's not too bad. All right, well, let's see if we can find that Jacobian.
You're muted.
All right, well, here's what we're going to have to do. We have to solve this system. Well, all right, add those two together. You're going to get, so we got u equals x minus v, or y, v equals x plus y. If I add those, I get u plus v equals 2x, or x equals 1/2 u plus v. There is my x equals in terms of u and v. I can do something similar if I subtract. So now I get u minus v equals minus 2y. So y is 1/2 v minus u. But now I can form my Jacobian. So dx du is 1/2. dx dv is 1/2. dy du minus 1/2. dy dv plus 1/2. So that gives us 1/4 minus a negative 1/4, which is 1/2. All right, well, there's our Jacobian. Now, we had to do some work to do this, to change this transformation. But look at what we ended up with as an integral. 0 to 2, 0 to 2, 1/2 u du dv. That one's so simple, I can do it in my head. It's okay if you can't do it in your head. But that ends up just being 2. Which was way easier of an integral once we did that transformation. All right, well, I see we're out of time. We're definitely not done talking Jacobians, so I still want to do more. So here's what's going to happen. The homework on Jacobians is not going to be due on Monday. I'm going to bump that forward as well. On Monday, we're going to do some more of this. I'm going to show you some more tricks. Like, for example, you don't have to do the solve for X and Y business. You can get around that if all you have is U and V equals. So we'll talk about that. We'll talk about other kinds of transformations, but we'll do some more Jacobians. And then we'll turn our attention to centers of mass and moments of inertia and some other applications of multiple integral. All right, so with that, are there any last questions on what I did here? Other than maybe the algebra of solving for X and Y, which I'll let you figure that out on your own. Okay, so with that, then I'm going to go ahead and stop the recording. And hold on one second.